All right, good evening, guys, and welcome back. We have been on a journey of calculus so far where we focusing on curve sketching. And I just want to say that it's important that at the stage you make sure you have a thorough understanding of the building blocks, the little topics which we have discussed so far. And I'm just want to take you through a quick recap, very important. At the stage, everyone must know how to find the derivative. And then we need to know or have at least a good understanding of what the derivative means. And I would have showed you something like this. Um, so, for example, if I've got a graph like this, maybe I'm being biased by just showing the positive x-axis, but it's okay. So if you've got a graph like that, and uh, I ask you where the graph is increasing or where the graph is decreasing, that kind of a thing, you need to be able to use the gradient test or the derivative test to tell whether it's increasing or decreasing. So I introduced you to the slope man. I could put up a straight line like that. I could put up one like that, one like that, one like that, and one like that. And we established a few things that whenever we draw a straight line at the turning points, what is interesting to note is that the derivative is a zero respectively. And this is one of the facts we will be using today. Here we know that if I substitute a point there, a point A in the derivative, and I get a positive answer, it means that the function is increasing at that particular point. All right, so this is very, very, very key for us to understand. But we did not only stop there. Another important fact that I need us to recall is that of the second derivative. This one was just a matter of discussing the first derivative. The second derivative is also powerful in that it informs us about the concavity of a cubic function, or not even just a cubic function, okay? If you've got a sketch, look at that. Look at that. It tells us whether this graph is going to be concave up or down, okay? So the green is obviously concave up, the orange is concave down, and right here, somewhere there is an interesting point called the point of inflection, where concavity changes from being concave down to being concave up. And to find that point of inflection, we actually determine the second derivative, which is basically linear or a straight line, and we set it equal to 0 to solve for x. And that x value becomes the x coordinate of the point of intersection. Sorry, not point of intersection, point of inflection. And for us to then find the y value of the point of inflection, we will substitute that x value into whatever the equation of f is. All right. Now, we then learned how to classify our stationary points. You would recall I said something like this turning point here being a local max and this turning point here being a local mean. What is actually interesting is that we can also use the second derivative to check whether a point is a local minimum or a local maximum. For example, right at this turning point, I know that the first derivative is equal to 0, okay? Let's call this point, the x value of this point, let's call it a. So I know that when I substitute a into the first derivative, I will get a 0. But now if I want to know whether this is a local max or a local mean, obviously here we can see it's a local mean, but sometimes you need to know whether it's a local mean or max before sketching the graph without a sketch, in other words. So I will then look for the second derivative at the exact same point. And what I anticipate for a local mean is that the second derivative should give me a positive number. All right, it should be positive, in other words. So when the second derivative is positive, we basically saying your graph has to be concave up, which means you have a local minimum. When the when the second derivative is negative at a point A, it means your graph has to be concave down, and that would mean you have a local max. So please beware of this. So let's call this one point B. So if f of B is negative, then I know I've got a local max. All right. And of course, here the derivative is still 0. There is another special point of inflection, which I think I should tell you all about. And this point of inflection occurs with some special cubic functions. For example, a cubic function like this. Oh, I'm in line mode. A cubic function like this will have a point of inflection somewhere there, roughly speaking. And what is interesting about this one is that it is not a local mean nor a local maximum. But there are two things, okay, that are actually happening here. What is actually happening here is that the first derivative is 0. The second derivative is also 0. And when we have such a case, where the first derivative and the second derivative are both 0 at the exact same point, that point actually is what we refer to as a stationary point of inflection. That's what we do, where we say about it. It is a stationary point of inflection. So it is very important that when you are given an expression for a function, you are actually able to tell whether you are dealing with a situation of a stationary point of inflection or just a normal point of inflection, which occurs where concavity changes, all right? So we get two types of points of inflections. Please take note of that, all right? Sometimes, again, we can get just a point of inflection where there are no stationary points. So it is possible to actually have a cubic function where there is no stationary point. All right, what I'm gonna do now is, I think I'll just do, I think, yeah, let's actually do an example where we have to bring all this together. So let's take this given. So we are given f of x is equal to negative 2x cubed plus 3x squared plus 12x. Let's leave it at that. Now, the first question is calculate the coordinates of the stationary point. Now remember, so let me just make this clear. We want to find the stationary point. So if I want the stationary point, I must actually find the first derivative and then equate it to 0, and then I solve for x. But take note, they want the coordinates, right? So the first derivative will be negative 6x squared plus a 6x plus a 12. This must be equated to 0. I'll divide by 6 because it is common. Then I'll get x squared minus x minus 2, which makes life slightly easier. So now I can factorize, and I establish now that there is a stationary point at x equals to 2 or x equals to negative 1. But because they want the coordinates, I have to substitute these into the original so that I get the corresponding y values. So f of 2 means I will substitute a 2 in the place of x. And I'm hoping that someone is doing this for me. Is going to tell me what f of 2 is. I hope you have your calculators. And then f of -1, we will also need to know what that is. So please, guys, as I write the substitution down, you do it in your calculator and you tell me exactly what these should be. Okay, is someone that need, or you, otherwise you can put it in the chat. But that's going to be a +2 plus a 3, that's a 5, 5 minus 12. Is that a -7? Okay, you will verify for me there. Please, guys, let's go. I hope you are all tuned in, then you can hear what I'm saying. I just need someone to find f of 2 for me. Right, f of 2, 20. Thank you so much. So which means 2 and 20 is one of our turning points. 2 and 20, and the other one is -1 and a 7. All right, very good. Now, guess what? The next question is classify. Okay, Elma, you've got your hand up. You are more than welcome to ask a question if you've got a question. Go for it.
No, sign. I understand why I wanted to ask a question, but it's fine now.
Oh, okay, cool. So number 2, we want to classify the stationary points. So in other words, we want to know between these two, which one is a local minimum, which one is a local max, or perhaps one is a stationary point of inflection. Well, let's classify them. Let's just quickly recap, guys. I want you to see this. All right. Remember, we're going to know it's a local max if the following happens. If we find the second derivative and we substitute the x value, and if we get a negative upon substituting the x value, that means the second derivative is well, that means we have a concave downward shape. But if we substitute the x value and we get a positive for the second derivative, it means we have a concave down situation. So let us actually see then what this means. Remember, these are the x values of the stationary points, so that 2 and the -1. But first of all, let's find the second derivative. We're just going to take the first derivative and derive it. That's how we calculate the second derivative. So this is our first derivative. So we're going to derive that to find the second derivative. So this must give us a -12x plus a 6. Now, let us do the substitution. I'm going to substitute into the second derivative a +2. And you're going to do that for me as well. Let's see. It looks like I'm going to have a -24 plus a 6. I don't know what that is. It looks like a -18. Somebody will confirm that for me. But surely -18 is less than 0. In other words, a -18 is a negative number. Of course it is. Now, if it is a negative number, then what should happen? It means that what is really happening at 2 is that we have a concave downward situation. And if we've got a concave downward situation, it would then mean that the point 2 and 20 is actually a local max. Then we're going to do the same thing with the -1. We're going to substitute a -1 into the second derivative. And I hope you see as well, that's actually a 12 plus a 6. Yes. And that looks like a +18, which is obviously a positive number. And what does that mean? We have a happy face there. And with a happy face comes a minimum. So we will happily say the point -1, -7 is actually a local minimum. So very, very important to take note of that. You see, without even a picture of the graph, we can now start to see what is happening here. Now, the third thing that we're going to do here is we're going to calculate the point of inflection. Point of inflection. Now, the point of inflection means that we take the second derivative and equate it to 0. All right, so what is our second derivative? It's a minus 12x plus 6. So the minus 12x plus a 6 must be equated to 0. So this means a negative 12x is a negative 6, so which means x is a half. Remember now, this is just an x coordinate of the point of inflection. To find the y coordinate, we have to substitute a half into the original. They want the coordinate, so we have to find the y coordinate as well. So once again, I'm going to ask someone to substitute, in other words, find f of half for me. What do we get when we substitute a half? So you're going to do this nicely and quickly into your calculator. That's a half. This one is squared. And then 12 times a half. All right, please go ahead. And I will wait for an answer from the first test. Let's go. All right, it looks like f of half is a 7, which means the point of inflection happens when x is a half and a 7. So that is very good. Now, another interesting one is, which is number 4. And I hope you all remember this. This is one of the very first few things we did well. I think one of the first things we did, I don't know if you remember when we were talking about cubic equations, okay? The next thing is determine the x-intercepts. So how do we find x-intercepts? So remember then, the expression f of x is essentially saying y. So this is actually saying y is equal to minus 2x cubed plus a 3x squared plus 12x. Now, it's important to note that in this situation, you actually have x as the highest common factor. And so we will go, you could actually, if you like, you could factorize a minus x instead of a positive, just so you have a positive x squared here. I think it will give you a peace of mind. But in any case, it's not a train smash because you also have access to the quadratic formula. Yeah, I probably have gone the hard way here. We don't have to stress because the quadratic formula is there. This is minus a 4. No, not at 4. Oh my word. It's a Sunday, guys. You'll excuse me. Right, great. That's that. So now remember, we got to apply the zero factor, or sorry, no, zero product principle, which says if A times B is 0, then either A is 0 or a B is 0. So this is, because you are finding intercepts, this is where you're going to say, well, either minus x is a 0 or 2x squared minus 3x minus a 12 is a 0, which means here x is a 0 because we just divide by negative 1. So 0 divided by anything, you get 0. And then here you can use the quadratic formula. I'm not sure. Or forgot to include the negative. Okay, we have changed. It's 13 over 2. Okay, thanks for verifying. Not a problem. 13 over 2 for f of half. 13 over 2. Let's take note of that. 13 over 2. Okay. Right. So here I'm going to just check if I can factorize this. If I can't, we'll use the quadratic. And then we want 4 will give me an 8, 4 and 3. 8 minus 3 is a 5 though. So 6 and 2, 4. Okay, which factors are going to work here? 3 is a 6, no. If I put a 6 here, that's not going to work. Okay. So that means I'm going to actually go with the quadratic formula here. I don't seem to get my factors. So someone is going to do this for me again. Minus 3 plus minus b squared is a 9. 4ac means you are multiplying 4 by 2, which is an 8, and then you are multiplying 8 by a 12. So that will give us a 96. So it makes sense why we couldn't get the factors here. So obviously this will become a plus 96. I hope I got my 4ac correct. 4ac would mean 4 times 2 times a 12. That's a 96. Now 96 plus a 9 is 105. So this is all over 2a. So yep, that's why we couldn't factorize, because 105 is not a perfect square. So you're gonna get decimals here. So and I just want to ask that somebody finds those for me. So x is a 0 or x is a what? Please get me those two numbers with your smart and lovely calculator. 3 plus square root of 105. Maybe I can use my emulator as well. Emulator, where are you? Here you are. Okay, so 3 plus square root of 105 over 4. So 3.3, roughly we are talking about 3.3, or x is equal to, we're going to put a negative here, negative 1.8, negative 1.8. So these are the three areas on the x-intercept where this graph will be crossing. Okay, very, very important to take note of that. As for the y-intercept, it's quite easy to see that it is 0, because you just need to substitute x equals to 0, and everything there surely is going to be 0. Now, I want us to actually try and sketch this. So let's sketch this. Today you're learning how to sketch a cubic. How nice is that? Let's sketch this. After sketching this, I'm going to share some generic principles with you, and then give you one to try on your own. I will share the principles. After sharing the principles, you will have to try one on your own. And when you have tried one on your own, and you are able to sketch it, I think we can successfully say we now have achieved the goal for today. All right, so let's get this done. Yeah, making, oh no, that doesn't help. Okay, cool. So I'm gonna just randomly set up a grid here, the Cartesian plane. It's not gonna be drawn to scale, because as you can see, I don't have enough space here. If you notice our local max, for example, the y value is a 20. So I'm not going to be able to get that on the All right, guys. Remember, if I go all mute and all that, you gotta let me know. It would just mean my microphone is off. Okay. What I was saying, I don't know if you heard me or not. We have calculated the intercepts. I hope I was audible by then, or at least you can see what's going on there. And then secondly, I am setting up the Cartesian plane here for us to actually sketch this graph and see how it looks like. We want to see how this information comes together. So I'm starting with the x-intercepts. One, we've got x equals to 0, then we've got x equals to 3.3. I'm just doing a rough sketch here, 1, 2, 3, 4. So maybe we could say 3.3 somewhere there. And then we have negative 1.8. So if this is a negative 1 and that's a negative 2, roughly somewhere there. Mine will not be drawn to scale. So that's 0, that is a 3.3, that's a negative 1.8. We have already established that the y-intercept is a 0, so there are no issues. What we need to pay attention to right now is that part of the local max and the local mean. We know the local max is at 2 and 20, so this is where the 2 is. So somewhere there, let's roughly say that's a 20. So let's say that's a 20. So that's somewhere there, I've got my local max. Then my local mean, we said, is going to be at negative 1 and negative 7. So here's a negative 1. So somewhere here, maybe there, somewhere here, negative 1 and negative 7, I've got my local minimum. Now let's talk about the point of inflection and see where about are we going to position the point of inflection. So if we take 13, we divide that by 2, it's a 6.5. So let's say, by the way, the x value is a half for the point of inflection. So there's half, 6 point something. Maybe let's say it is somewhere here. What that means, it means that this is where concavity changes. Now, at this stage, you should really now get a good idea of how your graph is going to look like. If this is a local max, then we are expecting concave down like that. And if there's a local mean, then we are expecting concave upward like that. But from here, where does it go? Surely it goes to 0. Surely it goes through the point of inflection, and that goes up there. And surely this goes down here to cross that x, to cross the x-axis at that particular x-intercept. And this one then surely has to go up like that. And bravo, that's your cubic function in this case. So I just need you to see why it is important to actually know the classification of stationary points, because that will inform the shape of your graph. You will know actually where you are turning. You know whether there should be concave up or concave down and all that. So of course, this is not drawn to scale, but this is acceptable. All right. Finally, I will then now officially show you the different types of cubic functions that you may encounter. And then from there, I will then give you an equation and ask you to actually sketch a cubic function there from. Okay, so let us first take note that a cubic function is a function of the form ax cubed plus bx squared plus cx plus d. And it's very important to note that the a, just like in the parabola, you know when a is positive, you say it's a smiley face. When a is negative, you said sad face. So the a in a cubic function, the a kind of tells the direction of your graph. So there are a number of possibilities again. When a is positive, your graph would actually be increasing like that. Okay, I like saying increasing here from left to right. Of course, you could also have a situation like this, where you have a stationary point of inflection, or you could have a situation like this, where you just have a point of inflection and there's no stationary point at all. In other words, if you are to find the first derivative here and solve for x, you're not going to find a real solution because there's no stationary point. So let me maybe try and differentiate between 2 and 3. They almost look like the same. So let me try and differentiate. Yeah, then this one goes more like that. Yeah, I hope you can now see the difference. So for all of these graphs, A is actually positive. Now, remember, there could be an instance where the constant B, the constant C, and D are 0. And in that case, then you could have a cubic function that is simply represented as ax cubed. You could have it like that. So I need you to be open-minded. Sometimes then you could just have a cubic function that is represented as what? Ax cubed plus bx squared. Sometimes it's an ax cubed plus a cx. At times it could be an ax cubed plus d. There's just variations to this, okay? And sometimes actually we could go like this, a, then we go x plus p cubed plus d like that, where the p and the d, just like the parabola, would kind of give you the point of inflection. So, but we're not gonna, actually I've barely seen that, but we will see. We will see if maybe this year the examiner would bring it. I don't know, but it's always a good idea to know this. Obviously then A negative would mean the opposite. So this one, instead of increasing, it goes like this. And if you think about it, that's the graph that we just dealt with. And indeed, let's check, is A negative? Yes, the coefficient of the cubed term is negative. So if A is negative, you gotta get that. And then this one also would go down like that, or would go, nope, almost the same here. Okay, like that, you get the idea. All right, so very important to note this. But beyond this, I also need you to note actually there are a number of special cases when it comes to cubic graphs as well. So I want to now bring your attention to what could potentially happen on the Cartesian plane, so that you are fully aware of this. Although yes, it's a cubic, just remember a cubic means you will have at most 3 intercepts. So it doesn't mean you'll always have 3 intercepts. It just says the maximum number of intercepts is 3. But it is possible that as you draw your cubic, sometimes this can happen. And I want you to note here that you have a situation where your stationary point will be found by the equation f prime of x equals to 0. But at the same time, let's call this point A. Let's call this point A. At the same time, f of A, not f prime, but f of A is 0. Which means you have a situation where a turning point happens to be also what? An intercept. When this happens, usually then your graph would go, your function can actually be factorized into something like this when that happens. So whenever you're gonna have a stationary point, which is an intercept, that's usually the situation in your factorizing. I'm saying this because you will need to factorize when you find the intercepts. Or just beware, if factorization is not your thing, just make a mental note that, hang on, for the same x value, I got 0 when substituting into the derivative and the original. That x value must be at a stationary point. I just thought I should make you aware of that. And of course, that's not the only way it happens. It could also happen like this. I mean, it could start with that and then it goes on like that. All right. So be fully aware of that. I need you to be aware of that. Right. Then without any further ado, I will give you a function to sketch. So You're going to try this on your own, and then we will do it together to just review, see if we are catching this. So consider g of x. So you're going to try this now. Consider g of x is equal to x cubed. Let's be kind. For a start, x cubed minus 2x squared minus 15x. And I need you to sketch this. But as you sketch this, guys, remember there are a few things that are important. You got to find all intercepts. Step one, all intercepts, meaning x and y intercepts, right? And secondly, you will have to find the stationary points. And as you find stationary points, do yourself a favor and classify them. Otherwise, if you don't want to classify them, you can already then decide on the shape based on the value of a here. And then lastly, you will find the point of inflection. And then I will also like to actually ask you to find x values for which g is increasing. And then obviously number 5 will be a repetition, but you will find x values for which g is decreasing. All right, please go ahead. Let's try this. Just 5 things to do. I will give you more than enough time, about 10 minutes maybe maximum, or if we push it, we might give it to 15 minutes. It's your first time trying all this. So I'll give you about that to try this, and then I will come in again, and then we just do corrections, see if we are catching this. All right, go ahead, guys. All the best. Whoever is done, if you finish, type in the chat so that I know it's time to review. All right. Okay. So g double prime is equal to, where is it now? The first derivative is 3x squared minus 4x minus 15. So this will be now 6x minus a 4, but I must solve for x when this is 0. So 6x equals to 4. So x is a 4 over 6, which will simplify to a 2 over 3. But I need a point, I need coordinates, so you're going to substitute the 4 over 3 into the original, the 2 over 3 into the original. And I don't know if it is there. Unakwa, you're going to do that for me again. What do you get when you do 4 over 3, when you substitute 4 over 3? Not 4 over 3, I keep saying 4 over 3. When you substitute 2 over 3, what do we get? Okay, I'll wait for that one. I thought you'd have it ready. You substitute 2 over 3 into the original equation. How's that going? Right. So that gives us a negative 286 over 27. A negative 286 over 27. So that becomes our point of inflection. So very weird, ugly numbers here, but it is what it is. That's what we got. So let's see so far what has happened. The y-intercept, you've got that. For the x-intercept, for the principal there, and then for the factorizing, and those 3 x values. And then for stationary points, for setting that equals to 0, and actually factorizing and maybe finding the x values and consequently the y values. That is good. And then the second derivative, equating it to 0 to get that x value and the y value. This should be your marks this far. Now, let us sketch this. As we sketch this, there's something for sure that we know. What we know is that based on the fact that a is a positive number, let's just check a few things here. I'm going to focus on the intercepts. So the origin is part of the story. And then we've got 5 and a negative 3. So negative 1, negative 2, negative 3. And a 5, 1, 2, 3, 4, 5. So whatever happens, this graph has to cross those 3 points on the x-axis. And then one of our turning points is negative 5 over 3 and a 14.81. That's what it is. So we just gotta approximate it. We're not gonna get plotted really to scale here. We just need 5 over 3 in a decimal form, something like 1 point something, I'm sure. So but it's a negative, right? So it's a negative. Since it's a negative, so this is negative 1. So it's going to be somewhere here, but then the y value is a 14. So surely it's somewhere there. This is not drawn to scale. And then the 3 and the 36, here is where 3 is. It's actually a minus 36, as you can see it. So somewhere there. Okay, not drawn to scale. So remember, we are anticipating a shape like that. Okay, so obviously this is the one turning point. There's the other turning point. Let's just consider the point of inflection now. The point of inflection occurs at 2 over 3, which is just 0 point something. And then as well as what? Negative 287. 287 divided by what? My word, by 27, 10 point something. So what is that turning point there? 14. Yeah, so very well somewhere there. The point of inflection is very well somewhere there. And remember, by the way, your y-intercept is a 0. So it must go through the origin like that, and then like that, like that, like that. So our point of inflection, I think, or I presume it will be somewhere there. That's no, I think, where is it? It should be 0 point something and a negative. So I got it wrong. That's not where it should be. Our point of inflection should not be there. So let's have this. It should be somewhere here. I think that's relatively fair because that's 0 point something, then minus, the y value is minus. So that makes sense. All right. So then we just show with the arrows that this goes on, and that's what g of x is. All right. So guys, you got this right. Well done. You made some mistakes. It's okay. We learn from mistakes. That's why we have sessions like this, so that we make all mistakes here and we don't make such mistakes in the final fixture where we do the exam. All right. So at the stage, what I will suggest is you go over the book one thingy, and then you try all the questions that require you to sketch this. Tabang, you've got a question?
Yes. At the x-intercepts,
Yes,
instead
Tabang.
of writing x equals to 0, I used difference of two squares, and it gave me x equals to 5 and x equals to negative 5.
But which did you use the exact same function we're using? How did you get there?
Like the normal way we use the method we use to find
the intercepts.
X-intercepts.
Yeah, maro
of normal cubic.
bona gore re ntseng. So I think you should have noted what x is your highest common factor. Yeah, you got to watch out there. X is your highest common factor. So you got to factor that out first. And then you are left with this quadratic here. In fact, Tabang, I want you to notice something. Whenever you have a function represented in this form where x appears in every term, take note there are 3 terms. And in each of the terms, there is an x. Whenever you have this kind of situation, you must know, noma kanjani. it will go through the origin. In other words, 0 has to be one of the intercepts.
Okay. But I still got everything else, right?
Yeah. Well done for that. Yeah. Just the one thing that's going to beat you here is the intercepts. So please try and pay attention to that. Okay. Try and pay attention.
Thank you.
Yeah. So guys, go and do the questions that are on sketching now. You should be able to do that. Don't do the ones where they want you to find the equation. That is our next talk, okay? Next talk, we're going to do the reverse process. For now, I want you to just go and sketch. That's all. And if you can do that, that will be great. Those are exam level type of questions. Of course, your textbook will also have some questions. You can try those as a way of building up to the ones on the past paper booklet. But well done for tuning in. Let's meet again next Sunday, the same time, and we're going to do the reverse process. We're going to be given a graph now, and we will be required to find some stuff, some points, maybe coordinates, or maybe find an equation. We will see. But let's go master this. The focus this week, go practice everything that has to do with sketching a function. Cheers, guys.